Hi everyone. So I was studying bitwise operators and working with bits in the Java, and the one problem struck into my mind that you know, how do computer deal with negative numbers? Because computer only knows bits, right? So it only knows ones and zeros. So how does the computer realizes when it is dealing with a negative number, right? So that was my issue. And I read about it and I thought I will make a video on it because it's a topic that I found a little interesting. So yeah, so in this video I'll be covering that how does computers understand and manages and deal with negative numbers, right? So let's start with it. So before starting with negative numbers, let's see like how in binary the positive numbers are dealt. So let's take example. Let's take 10 as an example, right? So we know for a fact that 1 byte is equals to 8 bits, right? That we know. So let's assume that the this integer value is stored in 1 byte. So that means it will be stored in 8 bits, right? So I'll make a structure 3, 4, 5, 6, 7, 8. So these 8 blocks represent the 8 bits in which the numbers would be stored. So now 10 would be stored like, so we have 8 here and 4 and 2 here, and we can just fill it with zeros. Right, so we know for a fact that the first place of the binary is 1, then 2, then 4, then 8, then 16, 32, 64, 128, right? So we know that. So 10 would be represented like this, right? So 10 in decimal would be represented like this in binary. That is quite simple, right? But there's a problem. Not a problem, but so let's see what is the range that we can, range of number that we can have if we are following this 8-bit pattern, right? I'll make this bit again, or I'll just remove it. Okay, yeah. So, never mind. I have to remove it all. Okay, so we'll make this empty bits again. 3, 4, 5, 6, 7, and 8. Okay. Now, what is the maximum number that we can get if we are using 8 bits to store the number, right? So to the maximum number would obviously, if we, so what's the smallest number? Smallest number would be nothing but this. All the bits are zero, so that comes out to be zero, right? Because all are zero, so all bits are zero, so the decimal number will also be zero. Now the maximum number that we can make would obviously be if we fill all the bits with the one. If we fill all the places with one, right? That would be the maximum number. Let's calculate what it would be come out to be. So it's 1 and 2 and 4 and 8 and 16, 32, 64 and 128. So 128, 64, 30, this comes out 96. This is 10, 12, 14, sorry, 15 and 31 and 128 and 120. It comes out to be 255, right? Right. So this whole sum comes out to be 255. So the maximum number that we can, why did I remove it? So the maximum number that we can get is 255, right? So the range comes out to be the minimum number was 0 and the maximum is 255, right? So if we are storing in 8 bits format, the minimum is 0 and maximum 255. We can store it in this way, and this is a range. So any number in between can be represented easily with this 8 bits, right? But here's the issue, right? We can only store unsigned numbers. Now, what does an unsigned number means? Is it that there's no sign? Signs means positive and negative. So we are getting 255, but we don't know if it's positive or it is negative, right? There's no way we can determine that if the number that we are dealing with is positive or negative. Like the computer doesn't know, right? Obviously, it doesn't know. It's only one and zero. How would it know if it's negative or positive? So the this problem was, this problem was uh, resolved by the mathematicians by following a very simple rule. I'll just remove this all. Right, so you do understand the range 0 from 255, right? I'll write it down again on the top. Okay, let's see the issue. What was the issue that I'm talking about? Issue. issue. The range came out to be 0 to 255, right? But the issue was that we don't know if the number is positive or negative, right? So how did how did we resolve it? It was very, very simple. So we had, 8 bits, right? I'll write it down here. So we had 8 bits, 3, 4, 5, 6, 7, and 8, right? So we had, uh, one second, let me just turn off my AC, turn it down a little bit. It's quite cold outside. Okay. So what we did, the mathematician came out with a system that we can just, so this bit, first of all, is called as MSB, and this one is called as LSB. It's least significant bit and most significant bit. And what does this means is that, any bit that would be, any number that would be, any bit, because 0 and 1, but that would be here, would be the least significant of the overall number, right? And what does that mean? That it would contribute less to the value of the whole number, of the number, right? Okay, so if I have one and, one or zero, the value would be one. It would contribute one because it's at the one place, right? But if it was here, the bit here would contribute to 128, right? So if it's one, it means it's set. The number would be incremented by 128, right? So it's more significant in terms of the value. I hope you understand it. It's just like that. It contributes more to the overall number, right? So that's most significant bit. Anyways, so the mathematician came that we can just reserve this bit for science. For science. So what does it mean? That we can represent, we can reserve this bit to represent positive or negative. And how does we represent positive? We can represent positive by just, having a zero, and negative by having a one. So that means that if the this bit, is one, the overall number that would be represented here, would be negative. But if it was zero, if it's zero, then the number that is represented here would be positive, right? Now there is a thing that, okay, so one thing I want you to know that is, because we have, removed a bit from here, the range that was 0 to 255 is now reduced, right? Because now let's see what's the maximum number that we can get. So we can just ignore this because it's gone, kind of. We can't use it really because it's just representing the number. So let's see what is the maximum number that we can get. So if we fill out all the digits, with all the bits with one, that's, where we can get the maximum number. So it was 128, but we are not using it. So 1, 2, 4, 8, 16, 32, and 64. 64, 36, 32, 96, 96 plus, 10112, right? 120, 124, 120, 126, 127, right? So it comes out to 127, right? So the maximum number now that we can represent here is not 255, but, oh, my bad, but it happened 127. So now range becomes 0 to 127, but it's both in positive and both in negative, right? So if I have, all the bits set, it would be, and, 0 here, it would be positive of 128. And if I have, 1 here, and because it's not contributing to the final value, but it's just showing the negative, or it's just showing the sign, right? So if all bits are set, it would be 127, and if it's a 1 here, I know that it's a 127 of negative. It's 127, 128, right? So the range comes out to be now 127 to 127, right? So that's the range that we come out to. But here's an issue, and I'll show you what the issue is. Um, so the issue was, very simple. Uh, Let me just remove it. Remove this. Mm, hmm. Oh, I don't. Yeah, there's a hotspot here. Mm, oh, mhm. Right. I'll just move it all. It's better to clean, all of them at one time than to, uh, go around and nitpicking all that. Okay, so I'll just, get the bits again. One, two, three, four, five, six, seven, and I'll represent this set bit, the sign bit with this, so that it's easy to understand. Okay, now we know that this is sign bit. We can't use it. Oh, this color. I want to make this as modular as it can get, so you can get an idea. Okay, so we can't use this bit, right? Okay, so we represented 127, we represent 127 and minus 127. Let's try to represent 0. Let's go. Let's, what's wrong with this pen? Right, yeah. So let's try to represent 0. Okay, so do the 0 comes out to be, so you can just, put all the values of 0, right? And so, and we can have a 1 here, right? Because it's not contributing to the value, right? And but here's an issue, right? We can have 1 here and we can have 0 here, right? So we can in this place we can have 1 or we can have 0. So the value of 0, so the value of 0 in decimal comes out to be, so the there's okay, okay. So what I want to say is that we can represent the decimal 0 into two ways in binary, right? In binary, understanding my point, right? So this whole value is 0, right? And we know for a fact that in this sign bit, we can have either 1 or we can have either 0. So there are two ways we can represent 0 in decimal, and that's wrong. That's confusing to computer, right? Okay, I'll show you what I mean. So 1, 2, 3, 4, 3, 4, 5, 6, 7. This represents 0, and 1, 2, 3, 4, 5, 6, 7, 8. This also represent to 0, right? Because the only thing we care about is this part, right? This part. The this part is sign bit. This doesn't contribute to value. And we if we check this part, this comes out to be 0, right? So there's an issue, right? There's a two numbers in binary that represent a single decimal single number, and we are also saying that there's a number. Either you can understand it this at this in this way, that there are two numbers representing 0, or you can say that, or you can also understand this as saying that there exist two numbers, one negative of 0 and other positive 0, right? You understand this point? Let me just erase it again because it's important. So 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7, 8. This is saying that we have a number that is a negative of 0, and this is saying that we have number positive of 0. But this doesn't, negative of 0 doesn't exist. There's no number as negative of 0. So this way of representing negative numbers is not correct, right? It's not correct because it is saying it is getting a number that doesn't exist. So we can't use this in computers because we can't, have any imaginary number or any number that doesn't exist. It would, result to many failures in programs, right? So there's no this way we can't represent on computers. So we had to find another way. We had to find another way. So the other way was quite simple. If you, I think so. You have know about it. So we know about the first complement, right? We heard of first complement. There are two concepts. I'm having issue with my pen. So we have first complement and yes, second complement. Now, what does complement means? Complement means, flipping the bits. Ah, had a pen, flipping the bits. So if we just flip the bits, that's first complement. We'll talk about the second complement further in this video. But let's talk about the first complement. Okay, so let's look at the problem that we were facing. Or let's before problem, let's look at the way how we get to first complement and how does it benefit to storing the negative number. So we still have those 8 bits 1, 2, 3, 4, 5, 6, 7, 8, and this is again reserved. So the 127, for example, so 1, 2, 3, 4, 5. It's so this is 127. We haven't yet decided if it's positive or negative. Let's keep it as positive of sorry, positive of positive 127, right? So it's positive 127. Now, how do we store negative number? Store a negative number of a number. You can just flip it straight, right? So you get the positive number first. So if you have to find minus 127, I would get the positive 127 and I'll place it down and I'll just flip the bit. I'll go first complement to it. Okay, so let's do the first complement. So we'll just flip all the bits. This would be zero. This would be zero, 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 and one.
So that's how we will represent the 127 in negative. That's how we do it. But again, that's an issue, right? Because now we have an issue. What the issue is, let's take some other example. Uh, so it works well for other numbers, but it would still fail for zero. Yeah, again, that's the case. I give you a filer, kind of. Not a filer, you know about it. So we'll have 1, 0, 1, and 0, 0, 0, 0, and 0. It's 5 in positive, right? So if you were to write it in negative 5, you will just flip the bit, right? This would be, so uh, this number is negative 5, right? Just flip the bit. But this first complement will also fail. Where? I'll tell you where it will fail. Okay, no, let's represent 0. So 0, 0, 3, 4, 5, 7, 8. So this is 0, and this is also 0. 3, 4, 5, 6, 7, 8. Right? This is also 0. Because complement of this is 3, is this, right? So this also, the problem of two zeros is still there, right? Still there. We still have two zeros because as I said that we can just, so we just need a way that we can, so now what the point of this is, what I'm trying to say, we just need a way in which we can eliminate minus of zero completely. You can see that this way we have something called as minus zero, but this doesn't exist, right? So if we are using this way, we are getting minus zero, but we don't want this minus zero. It's the issue that we are having. We want to eliminate this, you know, to the prevailing of this completely. We don't even want that even accidentally we get this number, right? Because that will be an issue in computer level. But if you code something like this word and minus zero comes, your whole calculation, your whole system is failed, right? So we can't have a system failure inside the thing that all the computers will be using, right? So we can't represent a negative number with the first complement too. We need another way. We need some any other way, right? So the other way was very simple. We can just use second complement, and I'll show you how it solves the issue of these two zeros, right? So we have second complement next, second complement, and and how does it work? We do the first complement, so the step of first complement fail, and then we add the plus one. Right. Let's look for a number. Let's look the number again 101 at 5, 4, 3, 5, 6, 7, 8. Right. So this is positive of 5. So to get negative of 5, we'll flip the bit 1, 2, 3, 4, 5. Right. And we'll add a plus 1. Right. So we'll add plus 1 in value. So 1 and all are 0. So 1, 1, 0, 1, 1, 1, 1, 1. This number represents negative of 5. Right. So you was like, okay, it works, but does it work for you? Now let's check it. Because as I told you, the only issue that we are having with all the methods that I told you would work fine all other numbers, but they would fail for the number zero. They would give you something as negative of zero, and that doesn't exist. So the only thing that we are looking for is to remove this negative zero completely. We don't want it to even accidentally come. Right? We don't want negative zero in our program to come even accidentally. Right? We don't want that happening. So, okay, let's see. Let's see. So let's represent the zero. So zero is 1, 2, 3, 4, 5, 6, 7, 8. Right? This is positive zero. Supposing positive zero. And I'm saying let's try to find the negative of zero, negative of zero. Because okay, there's no such thing as negative of zero, right? You know that, right? So what I want is that negative of zero should come out to be exactly same as zero, right? If I equate them, then it's simple, right? Negative of zero is like if we talk about in general way, negative of zero is same as zero. There's no, I know that there's no nothing as minus of zero, but in real life we can just say that they are equal, right? So whenever negative of zero comes, just give them the value of zero, right? Right. And that was the issue that we were having with other ways. Other ways,
So, so my idea is if minus of 0 is same as 0, we would, completely solve this issue. Let's try it. So I said we'll first do first complement. First complement is nothing but just flipping all the bits 4, 5, 6, 7, 8. Okay, so we are done with first complement, and this was an issue, right? Because it's giving some other value than the than this positive of 0. So negative of 0 and positive of 0 were two different numbers. But what I want is that minus of 0 should be equal to 0, but they are other different number, right? And same was the case with the original method in which we only had, the first bit as a sign, right? Let's see how would second complement fix this issue. Okay, so second complement, we did the first step, that is converting to first complement. Now we'll just add one and let's see. So, okay, I'll just remove this from here so that it becomes little clean. 2, 3, 4, 5, 6, 7, 8. We'll add it. So, okay, 1 plus 1 is, so 1 plus 1 is 2, and we can represent 2 is 1, 0, right? In binary. Okay, so it's 2, so 0 and 1. 1, 1 is 0. It's sorry, 2 again. 1, 1, 2, we'll take one carry. 1, 1, 2, 0 and 1 carry. 1, 1, 2, 2 and carry. 1, 1, 2 and 1 carry. 1, 1, 2, 0 and 1 carry. 1, 1, 2, 2 and carry. Right? So the number comes out to be this. And you'll be like, okay, you said that if this and this number equal, we'll be solving the issue. But this numbers are not equal. Well, they are equal. And I'll show you how. Okay, so I'll just remove this thing in between. Okay. Now I want you to count the numbers, right? The count the number that's we have. So we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 bits. And in here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. So we have 9 bits, right? So we have 9 bits. And you remember in starting I told you that we are storing the number in 8-bit format. So what happens is in binary, if a number exceeds the bit like that, so we have 8 places and it exceeds, and the number is coming up, the bit is the number is very long and it goes out the scope of the bits, it would be ignored, right? So the bit outside the 8-bit range would be ignored, right? So that's this case. So this would happen in this case also. So 1, 2, 3, 4, 5, 6, 7, 8. We have ever 8 bits till here. So the numbers, the bits from here would be ignored. So this one would be ignored. And now we will be left. So this would be ignored. I can just remove it. It's there, but it would be ignored. It would be, overflowed. So it will be overflowed by the range. You heard about the overflow, right? We see the integer overflow everywhere, right? So that's the case. So it will overflow, and the number we will be left with is this, right? And this is exactly the same as this. So this solves the issue of negative of 0 that was, that we were facing in first complement and other methods that we talked about in there. So that was it. That's how we represent negatives in the binary. So I'll give an quick overview. Uh, okay, so to summarize, there were three main systems, right? So the one we saw that the sign and magnitude, where the first digit was the positive or represent the positive or negative, right? And then we had the one complement, and then we had the second complement. The second complement one because it's simpler, this faster, and it avoids the double zero problem, right? Right? Because in other ways we were having the double zeros problem. So the second complement solved that issue. So that's negative numbers in two's complement, and that's how we store negative numbers in binary. So but that would be in next video because this video is getting longer. So I hope you guys liked it, and yeah, I'll see you in the next video.